Good morning. My dear students, in the last class we have discussed something about the electric field. What is electric field and how electric field will be represented we will discuss today. Last class we have discussed how the electric field for a point charges and how on which factor it depends. Does it depends upon the magnitude of charge or test charge or distance between them will be discussed in the previous class. Today we are going to discuss about the how we represent an electric field. So we have the electric field are represented by the set of imaginary lines. That is a completely hypothetical concept. That is, it is represented by a set of imaginary lines known as electric field lines, or otherwise it is also called as electric lines of force. Now, what is electric lines of force? When a positive charge, when a isolated positive charge is urged to move freely and to do so, then the path traced by the electric charge is called electric lines of force or electric field lines. So today's topic is electric field lines, or it is also called as electric lines of force. What is electric lines of force? If a positive charge is urged to move freely, the path traced by it is called electric lines of force. It is a set of imaginary lines traced by a unit isolated positive charge when urged to move freely and to do so. When a positive charge will be urged freely, the path, obviously the positive charge always moves towards negative charge or the negative plate. It means I would like to say that it is a set of imaginary lines traced by a unit isolated positive charge when urged to move freely and to do so. It always originates from positive charge and terminate at the negative charge. I would like to say that if it is a positive charge and it is a negative charge, then electric lines of force moves from positive to negative. Positive to negative. Electric field lines are continuous. Very, very important. Electric field lines are continuous. This is the CBSE questions regularly asked. If electric lines of force are not continuous, jodi continuous hei no thanda. If electric lines of force are not continuous, let us imagine this is discontinuous electric fields. It means it indicates that the point there is an absence of electric field, which is impossible. It means electric field lines are always continuous. Next, electric field lines are close to each other. That is, electric field lines per area directly proportional to strength of electric field. It means I would like to say that if electric lines of force are close to each other, they are very close to each other, it represents a strong electric field. If electric lines of force are far away from each other, then it represents a weak electric field. Clear? The tangent drawn at any point to the electric lines of force gives the magnitude of electric field, direction of electric, give the direction of electric field at that point. Let us imagine this is the point A. It means there is a tangent. This gives the direction of EA vector. Let this is the point B. This tangent gives electric field at B. Let this is the point C. Then EC vector. It means wherever you draw a tangent, it gives the direction of electric field at that point. It does not give any magnitude. Only direction will be provided by the tangent. Very, very important. Two electric field lines never intersect each other. It means, let us imagine this is an electric field line and this is another electric field line. So at a common point, I can draw this is an electric field and this is an electric field. It indicates there is a two electric field. There is a two electric field which is impossible. It means I would like to say that two electric field lines never intersect each other. If they intersect at the common point, there will be two tangent, that is two direction of electric field. Two direction of electric field, which is impossible. So it is not possible. If electric field lines are parallel and equidistant to each other, then it represents uniform electric field. Or else non-uniform. Just see. These lines are parallel to each other. These field lines are parallel to each other. Then and equidistant from each other. It represents uniform electric field. Listen to me. This is a reason and B is also another reason. Electric field lines moves from A to B. A to B means A must be positive charge and B must be negative charge. Now the questions. In A, according to this reason, the electric field lines are 3, and according to this area or this reason, there is also electric lines of force are 3. So I would like to say that here the lines of force are close to each other and they are apart from each other here. So, according to this point, electric field lines are close to each other. That is, electric field lines of force directly proportional to strength of field. I would like to say that if electric lines of force are close to each other, it represents strong electric field. So I can write it as a EA vector. Sorry, magnitude of the electric field at A is larger than the magnitude of electric field at B. Clear? So here the lines of force are close to each other, and here apart from each other. So electric field at A region is stronger, while electric field at B, and this is the point what we have mentioned here. So electric field lines are close to each other. That is, electric field lines are directly proportional to. So if it is close to each other, then it represents strong electric field. So close to each other it is for strong electric field. That is, electric field lines was area directly proportional to strength of electric field. Electric field lines are always perpendicular to surface of conductor and absent inside and absent inside hollow conductor. Let this is isolated positive charge. We have discussed that electric lines of force are moved away from positive charge. So this is for electric isolated positive charge. Let us imagine for a negative charge. Same thing. Electric lines of force are perpendicular to the surface of conductor, and moves towards negative. So this is for isolated negative charge. Like this is positive charge and this is positive charge. If for two like charges, electric lines of force are perpendicular to the surface of conductor and moves away from positive charge, it means this is. Similarly, I can draw away from positive charge. This is pair of like charges. I have taken two positive charges, that's why I mentioned positive. Clear? Similarly, I can take negative charges. This is also negative charge, this is also negative charge. Electric lines of force are perpendicular to the surface of conductor and moves towards negative. Moves. Clear? That is for pair of like charges and as I have taken negative, that is two like charges, that is negative. Similarly, I can take this is positive, and this is negative. So perpendicular to the surface of conductor, so they move from positive to negative. Electric field lines moves away from positive charge and towards negative charge. This is for pair of unlike charges. Clear? So electric field lines are continuous. Then the tangent drawn to the electric lines of force gives the direction of electric field at that point. Then two electric lines of force never intersect each other. If electric lines of force per unit area directly proportional to its strength, and then electric lines of force are perpendicular to the surface of conductor, moves away from positive charge and toward the negative charge. This is for isolated positive charge, this is for isolated negative charge, and this is for two like charges positive, two like charges negative, and this is for two unlike charges positive and negative. Now, listen carefully. Whenever we have taken positive charges or like charges, in between the two like charges, what happens? There is some lateral pressure acts in between the two charges. That's why, due to the lateral pressure, they move away. Due to the lateral pressure, they move away, and two like charges exhibit lateral pressure. So, like charges repel each other. To unlike charges, due to lateral pressure, they repel. To unlike charges, exhibit a longitudinal force. So they attract each other. Listen to me. When there is a force act in such direction, there will be a force that is called the longitudinal force. Clear? So if the longitudinal force will be act in such a direction along its lengthwise, then the two charges come closer to each other. That is, they attract each other. Clear? From a unit positive charge, four pi lines of force are generated. Clear? This is about the properties of electric lines of force. Some questions related to it. Draw electric field lines if a positive charge, this is the CBSE 2018, I hope. Draw the electric field lines if a positive charge is placed at a distance from a metallic conductor. Draw electric field lines if a positive charge is placed at a distance from a metallic conductor. Let us imagine this is positive charge and a metallic sheet will be placed at a distance from a. So as we know that electric field lines are perpendicular to the surface of the surface of the conductor, and it is perpendicular to the surface of conductor and it moves away from the positive charge. So as it is a positive charge, the electric field lines will be in such direction, perpendicular. Clear? If the question arises, if the conductor is a negative, similarly you can write it. Note for negative charge. Again, surface perpendicular to the surface of conductor, perpendicular to the, and moves towards negative charge. Clear? How can you produce uniform electric field? Let us imagine this charges. This sheet is positively charged. I have taken another sheet, negative charge. As we know that electric lines of force are perpendicular to the surface of conductor and it moves from positive to negative. So here the electric field lines will be in such a direction. Hence they are parallel and equidistant, and that represent uniform electric field. Can two electrified lines are ever intersect each other? Ever intersect each other? Can two electric field lines ever intersect each other? Answer: no. They never intersect each other. Because we have discussed earlier, if two electric field lines intersect each other at the common point, there will be two tangent, that is two direction of electric field, because the tangent drawn at any point to the field lines gives the direction of electric field at that point. It means at the common point there will be two tangent. They never intersect each other. If so, at the common point there will be two tangent, that is two direction of electric field lines. Okay, electric field lines. That is never not possible. Some general questions. This is the hollow conductor. For a hollow conductor, which electric field lines is correct? Listen carefully. For a hollow conductor, which electric field lines is correct? I would like to say that here 4 electric lines of force are. We have to know that, and electric field lines inside hollow conductor. Perpendicular to surface of conductor. Electric field lines inside hollow conductor are absent. Inside hollow conductor there is no electric field lines, and electric field lines are perpendicular to the surface. Listen carefully. Here it is not perpendicular. Theta is not equal to pi by 2. So it is not possible. It is perpendicular but inside exists. So this is also not possible. Look at D. It may be perpendicular but exists inside the conductor. So this is also not possible. Answer is C. Okay. Electric field lines inside hollow conductor are absent, because in case of C there is no electric field lines inside the hollow conductor, and electric field lines are perpendicular. Perpendicular means here electric field lines are perpendicular to the surface of conductor. Perpendicular. So option C is correct as compared to other. Electric field lines move from A to B. Four options are there. Electric field lines moves from A to B. A2 moves. It means we have already discussed electric field lines always moves from A to B, means A must be positive, because electric field lines moves from positive to negative. So A must be positive. Now, in case of B, they are close to each other compared to A. Hence, electric field at B is stronger. Electric field at B is stronger. A is small and B is negative. So this is the right answer. And this is also right answer. Because if is larger and A is positive, moves from. So these two options are right. Okay. This is about electric field lines. Next class we will discuss about the electric dipole. Thanks for watching to one and all. All the best.